So, in order for us to define a subgame perfect Nash equilibrium in this context, we must first define what a subgame is. Okay. Um, so, let us define what a subgame is. So, subgame basically refers to the game, a subset of the tree that come out of a specific node which is not which come out of the node of the game, which can be the initial node. It need not be the initial node. So suppose think about the game that comes out of that follows from this node where one is located. So I am referring to this part of the game. So this part of the game follows from this specific node, and therefore this sub part of the entire game is called a sub game of the initial game. Now the node can be the initial node also, the starting node. If it's the initial node, if it is this node, this is the initial node, then the entire game is a sub game. So that's why I didn't mention that it need not be, sub game can be starting from the initial node as well as a non-initial node as well. So if it starts from the initial node, then the entire game is a sub game. If it starts from any other node, then the game that sort of follows from that node it would be called a sub game. But there is a condition. What is the condition? The condition is that the nodes that come after the node that you are starting from. So suppose you starting from this node, these nodes are called initiating nodes. These nodes are called initiating nodes, or initiating node, because this is your starting node. The nodes that follow from the initiating node, the node that you can reach from the initiating node are its successors. Okay, the successor nodes. So this top node and this bottom node are the successor nodes. So let me just introduce these terms. These are successor nodes. So the successor nodes, so what is the condition? That the successor nodes must not be in any information set that contains some other node which is not a successor of the initiating node. Okay. So all successors of an initiating node must be in information sets that do not contain any other node that is not a successor. If that is the case, then the game that follows from an initiating node, the sub part of the game that follows from the initiating node is referred to as a sub game. So so basically sub game is the part of the game that follows from any node, follows from any node provided the successors are not in any information set containing containing nodes which are not successor. Sorry, it's bit. So this is the definition of subgame. So let's consider this game first. So this game, the node, the part of the game that follows from this node is a subgame, because all the two successors, the two successor nodes of this initiating node are in an information set that do not contain any other node that is not a successor of this initiating node. Okay, so successors are nodes of an initiating nodes. And but I can think about games where that is not true. So suppose, let's consider a kind of a complicated game that will not solve now, but we can come back to it later. But just to sort of illustrate that sometimes you can come up with complicated games where there is no subgame except the entire game. Okay, so suppose one plays either U or D, then two plays either A or B on the top, and either C or D in the bottom. If two plays A, then one can again choose E or F. If two plays B, then there's a third player that comes into the picture. Sorry, there's a third player that comes into the picture, player number 3, who can choose either G or H. If 2 chooses C, then the third player moves, and also can choose G or H. And if it's D, then the game ends. The let me now draw the information set. And the payoffs are 3, 3, 6. So there are 3 players, so I have to specify 3 payoffs: 1, 5, 7, 2, 0, 3, 7, 7, 2, 0, 6, 1, 8, 6, 0, 6, 2, 4. Okay, now consider this game. It's a complicated game. There are 3 players, but player 3 moves only in here and here, but player 3 has no clue what happened before. Basically, that's what this game is saying. By making this dotted line, what we are saying is that player 3 doesn't know whether it's in the top node or the bottom node, which means player 3 doesn't know whether 1 has played U and then 2 has played B, or whether 1 has played D and then 2 has played C, because these are the only 2 circumstances in which 3 moves. In all other cases, 3 has no 3 doesn't make a move. So when 3 realizes that it is his time to make a move, he knows that either the play has been like this or the play has been like this, because in all other cases 3 doesn't get a chance to move, right? So when 3 realizes that it's his chance to move, he knows that it's one of the 2 possibilities, but he has no clue what has happened. So basically, then 3 would make a choice for 3 would have to specify an action for this entire information set. Okay, 3 will say, I'll choose G if it's my chance to move, in which case this will happen. Whether it's sitting on the top node or the bottom node, G will be chosen. Or 3 can say, I'll choose H. Okay. Now consider what kind of sub games does this game have. Okay. So can we have a subgame starting from this node? The answer is no. Why? Because what are the successor nodes of this? The successor nodes of this are this and this, correct? However, this successor node is contained in an information set that contains another node which is not this initial node successor. So this is my initiating nodes now. Initiating node, and these are my successor nodes, right? This and this are successor nodes. However, it has this node. One of the node is contained in an information set which has this other node which is not a successor of the initiating node. Successor nodes are always related to an initiating node. You have a successor to an initiator of the initiating node, right? So then there is no subgame starting from this. Similarly, there is no subgame starting from this node as well, because the successor, there is only one successor node which is here, but it again contains it is in an information set which contains this another node which is not a successor of this node. Okay, so none of these are subgames. There is a subgame here. This is a subgame. Why? Because there are no successor nodes. So basically, by trivially, the condition is true. If there are no successor nodes, then all successor nodes basically satisfy that definition. So then this can be an initiating node, and this part of the game is a subgame, and the other subgame is the entire game. So the entire game is a subgame of the big original game, right? It's like a subset idea. The original subset is a subset of the original set. So the set is a subset of itself, but there can be proper subsets. So similarly here we can have proper subgames. So the only proper subgame in this game is this. There is no other proper subgames, right? Because of this condition, right? So hence this condition that is important to keep in mind, that provided the successors are not in any information set containing nodes which are not successors. Okay, so that you have to keep in mind. So so in this game now, so therefore there is only one proper subgame, and there are two subgames containing the original game itself. Okay, so now that you have some idea about a subgame, and we'll sort of continue to give examples to familiarize yourself with the idea. So let me now define what is a subgame perfect Nash equilibrium. Subgame perfect Nash equilibrium. So a subgame perfect Nash equilibrium so a profile of strategies, and one strategy for each player, that's a profile of strategies. A profile of strategies constitute a subgame perfect Nash equilibrium if it induces a Nash equilibrium in every subgame of the game. Okay. So a set of strategies or profile of strategies is a subgame perfect Nash equilibrium if it induces a Nash equilibrium in every subgame of the game. You notice that the original game is a subgame of itself. So that ensures that we are looking at Nash equilibrium of the original game, but we are only so the subgame perfect Nash equilibrium are the only Nash equilibrium of the original game that induces a Nash equilibrium in the proper subgames of that game as well, right? So it has to be a Nash equilibrium of the original game, but it has to also be induce Nash equilibria in the subgames, in the proper subgames of the game. Okay. Now, this definition is different from our previous definition, which said that a profile of strategies would be an SPNE if it satisfies backward induction, right? So we used backward induction before to define SPNE, but now we are giving a different definition. Turns out these two definitions are same in cases where you can apply backward induction, right? So this definition actually implies our previous definition in games where you can apply backward induction, and I'll demonstrate that using one of the examples that we did in the previous class. Okay, but let's use this definition in this game first. Okay, so in this game we must first pick a Nash equilibrium of the original game, because the original game is a subgame of itself, and then focus on Nash equilibria which actually induce a Nash equilibrium in the subgame. So notice this has a subgame here, sorry, not in this, this is a subgame. So this is the subgame, proper subgame. So it must, the Nash equilibrium of the original game must be a Nash equilibrium in the proper subgame. Okay, that's the idea. Oops, sorry. So for reference sake, let me draw the game again. Payoffs are 3 4 1 4 2 1 2 0, right? So it is a subgame, there's a subgame here, sorry, it's an information set here, and there is a subgame here. Okay, now what are the strategies in the original game? In the original game, one moves once here, one moves once here, and then again here. So one has to specify an action in all the information sets, or for one's case, since all the information sets are singleton nodes, for the two singleton nodes. So one strategies are UA is a strategy, right? Basically it's saying I'll choose U when I'm in this node, and I'll choose A when I'm in this node. So UA is one strategy for player one. Similarly, UB is another strategy. DA is another strategy. Again, notice that even if player one, given that player one is saying that it will choose D in the initial node, the game ends, but still one has to specify an action in the second node, right? So DA is a third possibility, and similarly DB. Okay. How about player 2? Player 2 can choose either X or Y. Notice I'm not saying, I'm not specifying two actions for the two nodes of 2. So 2 moves in 2 nodes, but I'm only specifying one action because, again, because 2 cannot differentiate between the top and the bottom node. They are in only one information set, and strategy's definition is now one action per information set, right? So 2 can only say that, okay, I'm in this information set, so I can only choose X or Y. I don't know whether I'm in the top or the bottom, so I cannot have a plan of action which is conditional on the node, but it has conditional on the information set, right? So 2 strategy is either X or Y. Okay, what are the payoffs? So let me write down the payoffs. If it is UAX, then it is 3 4. If it is UAY, then it is 1 4. If it is UBX, then it is 2 1. If it is UBY, then it is 2 0. If it is D, then it doesn't matter what the rest of the strategies are, it's 2 6 everywhere. Okay, let's look at Nash equilibria of this game. Okay, so suppose 2 chooses X. So here I have player 2, and here I have player 1. So suppose 2 chooses X, so then UA is a best response, okay, for player 1. If player 1 chooses UA, 2 is indifferent between choosing X or Y, so X is a best response. So this is a Nash equilibrium. Correct. If 2 chooses Y, then 1 is indifferent across UB, DA, and DB. And if 1 chooses DA, then 2's best response. So suppose 1 choose DA. If 1 chooses DA, then 2 is indifferent between X and Y, so Y is a best response. So suppose 2 chooses Y and 1 plays DA, and if 1 chooses DA, then Y is a best response. So this is also a Nash equilibrium of the game. By that logic, this is also another Nash equilibrium. Okay, right? So this original game has 3 Nash equilibria, but which one is subgame perfect? For that, we have to see what is the Nash equilibrium of the subgame. So let's consider this subgame. This is a subgame. Okay, so let's consider what is the Nash equilibrium if we think that itself is a game. So let me write down the strategies in that subgame. So in that subgame, 1 moves only once and can choose either A or B. So 1 can choose either A or B. This is for the subgame. And 2 can choose X or Y. 2 can choose, sorry, 2 can still choose X or Y, player 2. This is the subgame analysis. And what are the payoffs? The payoffs are 3 4. For AX, AY is 1 4. BX is 2 1. BY is 2 0. Okay. And if you see, this game has only one Nash equilibrium. If 2 chooses X, the best response for player 1 is to choose A. If 2A1 chooses A, then X is a best response for player 2. So AX is a Nash equilibrium, but there is no other Nash equilibrium, right? So now the question is, which strategy of the original game, which Nash equilibrium of the original game is consistent with AX being played in the subgame? Because AX, so let me just write AX is the Nash equilibrium in the subgame. Okay, so given that AX is the Nash equilibrium of the subgame, which Nash equilibrium in the original game, in here, which Nash equilibrium of the original game is consistent with playing AX in the subgame? This Nash equilibrium, right? Because in other Nash equilibria, like this one or this one, this is not consistent with playing AX in the subgame. Only this induces playing AX in the subgame. So that's what I am saying, that we have to look for Nash equilibria of the original game that induces a Nash equilibrium in the subgame. So playing UA comma X, that Nash equilibrium induces playing AX in the subgame, which is a Nash equilibrium of that subgame, right? Therefore UA comma X, oops, UA comma X is a subgame perfect Nash equilibrium of the game. Okay, so how do we find out subgame perfect Nash equilibrium? The subgame perfect Nash equilibrium must be a Nash equilibrium of the original game. So we drop the original game in normal form and look at all the Nash equilibria, and then we find out what are the Nash equilibria in all the subgames. So this game in front of us has only one subgame, so we look at the strategies in that subgame and find out which one is a Nash equilibrium. So AX we find is the Nash equilibrium in the subgame, and then we see which Nash equilibrium of the original game leads to or induces the players to choose the Nash equilibrium of the subgame. Okay, and so those the Nash equilibrium of the original game that induces or leads the player to choose a Nash equilibrium in the subgame is referred to as the subgame perfect Nash equilibrium, because this is ensuring that in all subgames of the game the player is playing a subgame perfect Nash equilibrium. Sorry, in all the subgames the player is playing a subgame, a Nash equilibrium. Okay, now this is, as I said, is different from applying backward induction logic and picking that Nash equilibrium that satisfy backward induction. But as I was saying, this way of finding an SPNE would imply the SPNE that you would find using backward induction in games where you could apply backward induction, because in games where you could apply backward induction you could still apply our current definition, which is the standard definition of SPNE. Okay, so the idea is that the game, the SPNE or the Nash equilibrium that induces Nash equilibria in all subgames satisfy backward induction. Okay, so that's the idea. I'm not showing you a proof of this claim, but this is true, and I can demonstrate this using one of the examples we did in the class, in the previous class. So let me go back to some of the notes of the previous class. So let's use this one. So consider, so this game we had analyzed in the previous class. It has this complicated strategies for player one, because player one was moving 5 times. Okay, so that's why it had to specify 5 actions. Okay, so this is a extensive form game. Here there are no non-trivial information sets. All information sets contain only one node. Okay, and we could apply backward induction, right? Now the thing is that we could still apply our current definition of subgame perfect Nash equilibrium in this game as well, right? Because in this game we can check what are the subgames, and check whether the what are the Nash equilibrium in those subgames, right? So this idea of subgame you can apply in all extensive form games. So let me first identify what are the subgames. So what are the proper subgames? So first you can see that this is a proper subgame. Okay, because it all the successor nodes starting from this initiating node are contained, do not have any information set containing any other non-successor node. Okay, because it's sort of very clear to see. The other is of course here. So this is another subgame, proper subgame, starting the initiating node being this. Okay, these are subgames. The terminal nodes are subgames as well. Like this is a subgame, this is a subgame. But here it will be it will be trivially the case that, so here Nash equilibrium in this, there is only one player. So how can we induce a Nash equilibrium in a subgame when there is only one player moving in that subgame? You just, here the Nash equilibrium basically means that the player is choosing the strategy that gives him the highest payoff. Okay, so that's, it's choosing an optimal action. That basically is what we would think of as Nash equilibrium in these games, subgames initiated from at the terminal node. Okay. Now, what are the Nash equilibrium in these big subgame, proper subgames, starting with these nodes where player 2 moves. So let me rub this. Sorry. And draw up the payoffs here. So suppose we are considering first this subgame. So in this subgame, 2 has two strategies, C or D, player 2, and 1 has two strategies, either G in the top or I, right? And H in the other option, or J in the bottom. So I'm sort of the choices must be same, the actions must be same for me to write down. So that's why I'm relabeling I and J as action G and H respectively, right? And the payoffs are 3,8, sorry, 3,8. In case of D it is 1,2, and here it is 7,9, and it is 2,1. Okay. Now what is the Nash equilibrium here? If 2 chooses C, 1 would like to choose H or J, and if 1 chooses H or J, 2 would like to choose C. Okay, so this is a Nash equilibrium. Okay, so CH specifically, so CH is a Nash equilibrium in that subgame. What is the subgame in the bottom node, starting from the bottom node? So again, the choices for 2 are EF, and for 1 is K or M. I'm relabeling M as K. L or N. I'm relabeling L as N. Sorry, N as L. And the payoffs are, if it is EK, then it is 10-4. If it is FK, it is 4-0. If it is EL, it is 0-5, and then here it is 8-3. Okay. So suppose 2 chooses E, then one would like to choose K, but and if if one chooses K, 2 would like to choose E. So this is, sorry, this is a sub game, Nash equilibrium. Is there another Nash equilibrium? If one chooses F, sorry, if 2 chooses F, one would like to choose L. If one chooses L, 2 would not like to choose F. Okay, so this has only one Nash equilibrium. In the top one, did we miss another any Nash equilibrium? If 2 chooses D, no. So in the two sub games, these are the strategies these are the Nash equilibria, right? Now check whether the original subgame perfect Nash equilibrium that we had identified using backward induction, that is written above, whether that induces these Nash equilibria. So notice that 2 is choosing C in this subgame as part of the Nash equilibrium strategy, and 2 is choosing E as part of this the bottom subgame Nash equilibrium strategy. And you see in the sub SPNE written above, there is CE, right? So CE induces player 2 to choose C in the top node and E in the bottom node. That is consistent with the Nash equilibriums in those subgames. Okay. Similarly, one chooses H and J, and you see H and J being chosen here. And again, in the bottom one is choosing K on the top node, N on the bottom node. But the Nash equilibrium that is induced is EK, so which is this. So the game that is in the bottom sub game, the play is given by 2 chooses E, then 1 chooses K, which is exactly this Nash equilibrium. So you see that the backward induction, the SPNE that we got from applying a backward induction in this game satisfy our current definition, that it picks Nash equilibria in all the sub games. Okay. So these two definitions you can apply either one when I give you a game where you can apply backward induction. Basically any game which doesn't have any non-trivial information set. Okay. So there applying backward induction is easier, so that's why we did that case first. And now we are doing the more sort of complicated case where you could you cannot apply backward induction, so you have to go through this process of checking which Nash equilibrium of the original game picks Nash equilibria in all the sub games. Okay, so hence this process. So in games like these that we have covered today, we have to apply the current definition. Okay, but this current definition you can apply in games that we had covered in the previous class as well, and it will give you the same result as backward induction. Okay, so in the third part I'm going to talk about the games where the strategies are continuous. Okay, so here the actions are continuous. Here actions are discrete, you choose either up or down, 2 chooses either A or B. So I'm going to consider cases where it's continuous. Okay, so let me stop here.